An input device is any hardware that puts data into a computer system, and every one of them does the same job in outline. Something physical in the real world, light, pressure, sound, movement, is measured and converted into the binary the processor can work with. Now, before we go through them, one piece of exam advice that matters more than any individual device. Questions in this section very rarely ask what a device is for. Everyone knows what a keyboard is for. They ask how it works, and they are marked on the sequence of steps in order. So as we go through each device, what you are learning is a short process. This happens, then this, not a description. If you can recite the steps in order, you will pick up marks that most candidates lose because most candidates write a sentence describing the device and stop. Start with the barcode scanner because it is the clearest example of that pattern. A barcode is a series of dark and light lines of varying thickness which together represent a number. Notice the word number because it is doing a lot of work in a moment. Let me take you through what happens when one is scanned. First, a light source, an LED or a laser, is shown onto the barcode. Second, that light is reflected back off the pattern, and here is the physical principle the whole device rests on. The dark bars reflect less light, and the light bars reflect more. That difference is the data. Third, sensors called photodiodes detect the varying reflected light and produce a varying electrical signal from it. Fourth, that signal is converted into a binary number. Fifth, and this is the step people leave out, that number is used to look the item up in a database. And sixth, the database returns the product's price and description, and the stock level for that item is automatically reduced by 1. Now, that fifth step is where a very common misconception lives, so let me be explicit about it. The price is not stored in the barcode. The barcode holds only a number that identifies the product. The price lives in the database record that the number points to. And once you see that, something about shops makes sense. It is why a supermarket can change the price of an item without reprinting a single label. They change one database record. The advantages follow from that. Scanning is far faster than typing a code in, and it is far more accurate, because no human has to read a number off a label and retype it correctly. And stock control updates itself in real time, without anyone counting anything. The disadvantages follow just as directly. A barcode that is creased, dirty, or torn will not scan at all. It holds only a small amount of data, typically a 13-digit number, and it is completely useless without the database it points into. The scanner alone tells you nothing. A QR code, that stands for Quick Response, is a matrix of black and white squares, and the key difference from a barcode is dimensional. A barcode stores its data along one dimension, the widths of lines across a strip. A QR code stores data in 2 dimensions across an area. That is why it holds thousands of characters where a barcode holds a dozen or so digits. Reading one works like this. A camera, usually in a phone, captures an image of the code. Software finds the 3 large squares in the corners, which tell it the code's position and orientation. That is why you can scan a QR code upside down or at an angle, and it still works. Then the pattern of light and dark squares is decoded into binary and into whatever data it represents, most often a web address. QR codes also carry built-in error correction, so a code that is partly dirty, damaged, or has a logo printed over the middle of it will still scan correctly. There is one disadvantage of QR codes worth knowing properly, because examiners like it and because it is genuinely true of the thing in your pocket. A QR code is not human readable. You cannot look at a grid of black and white squares and tell where it leads. With a printed web address, you can at least read it before you click. So, a malicious QR code, a sticker placed over a real one on a parking meter or a restaurant table, for instance, can send you to a convincing fake site designed to capture your card details or login, and nothing about the code itself warns you. That unreadability is not a curiosity, It is a real security weakness, and it is worth stating as one. A digital camera, light enters through the lens, which focuses it onto an image sensor, a CCD or CMOS chip. The surface of that sensor is divided into millions of tiny light-sensitive elements, and those are the pixels. Each pixel produces an electrical charge proportional to the amount of light falling on it. More light, more charge. An analog to digital converter then turns each of those charges into a binary value, and the camera's processor assembles all of them into an image file, usually compressing it, and writes it to a memory card. The number of pixels is the camera's resolution, and the trade-off is the obvious one. More pixels means more detail and a larger file. The keyboard is simpler than people expect. Pressing a key completes a circuit underneath it. The keyboard's own processor detects which circuit in the key matrix has closed, looks that position up in a character map to find the matching character code, ASCII for example, and sends that code to the computer. It is reliable and needs no training, but it is slow for large volumes of data compared with automatic input. Typing introduces errors that scanning would not, and prolonged use is associated with repetitive strain injury. An optical mouse works by comparison. An LED underneath illuminates the surface. A tiny sensor captures thousands of images of that surface every second, and a processor compares consecutive images to work out which direction the mouse moved and how far. Because there is no ball and no moving parts, it does not collect dirt and never needs cleaning, and it is more accurate than the mechanical mouse it replaced. It struggles on glass or a plain glossy surface, though, with no detail in the images, there is nothing for it to compare. A microphone. Sound waves reach a diaphragm and make it vibrate. That vibration is converted into a varying electric current, an analog signal whose shape follows the sound wave. An ADC then samples that signal at regular intervals and converts each sample to binary. How closely the digital version matches the original depends on the sampling rate, meaning how often samples are taken, and the sampling resolution, meaning how many bits are used for each one. A 2D scanner, usually a flatbed, digitizes a flat page. The document goes face down on the glass, a bright light illuminates it, while a scan head travels along its length. Mirrors and lenses direct the reflected light onto a CCD, and the CCD converts that light into electrical signals, which are digitized into a bitmap image. And note what you have at the end of that, a picture of the page. If you want text, you can actually edit. OCR software, optical character recognition, has to process the image and identify the characters in it. That is a separate step and a separate mark. A 3D scanner captures the shape of a solid object rather than a flat surface. It scans the object using lasers or white light, or in medical use X-rays and CT scanning. It records the position of a very large number of points on the object's surface, measuring its X, Y, and Z dimensions, and software builds those measurements into a 3D model. That model can then be edited, stored, or sent to a 3D printer to produce a physical copy, which is the link between this lesson and the next one. It is used for medical prosthetics and dentistry, for reverse engineering parts that no longer have drawings, in archaeology to record artifacts without handling them, and in animation and visual effects. Finally, touchscreens, which are both an input and an output device. The syllabus names 3 technologies, and they are told apart by what physically happens when your finger lands on the glass. A resistive screen has 2 transparent conductive layers separated by a thin gap. Pressing the flexible top layer makes it touch the bottom layer, completing a circuit at that point, and the change in voltage gives the coordinates, so resistive detects pressure. A capacitive screen has a glass layer coated with a transparent conductor holding a uniform electrostatic charge. Your finger conducts electricity, so touching the screen changes the electrostatic field at that point, and measuring that change gives the coordinates. So capacitive detects a change in the electrostatic field, which is exactly why an ordinary glove does not work on your phone. The glove is not conductive, so the field does not change. An infrared screen has emitters and detectors around the edge, creating an invisible grid of infrared beams just above the surface. Touching it breaks one beam horizontally and one vertically, and those two tell you where the touch was. So infrared detects broken light beams, and because it detects an obstruction rather than a property of your finger, it works with absolutely anything: a gloved hand, a stylus, the end of a pencil. Put them side by side, and each one's weakness is the price of its strength. Resistive is the cheapest and works with gloves or any stylus, but the flexible top layer wears and scratches. Sunlight visibility is poorer through the extra layers, and it cannot do multi-touch. Capacitive is durable solid glass, has good visibility and supports multi-touch, but needs a conductive touch. Infrared works with anything and supports multi-touch and large sizes, but it is the most expensive, and dirt or strong light can interfere with the beams. So when a question gives you a scenario, choose from the named property. An outdoor or industrial terminal used with gloves points to resistive or infrared. A phone that needs pinch to zoom points to capacitive. A large interactive whiteboard points to infrared. Two last things to carry into the exam. Describe the process in order. For the barcode scanner, that is light source, then the reflection difference, then the sensor, then binary, then the database lookup. And remember, the price is not in the barcode.